Hello dear students, this is our next derivation, derivation number 5. This is under the category of Gauss law derivations, and this is electric field due to a uniformly charged spherical shell. Okay, so let's start with the spherical shell which is uniformly charged, and this charge is Q. This charge Q is uniformly distributed over the surface of this spherical shell. The radius of the sphere is capital R, and we are taking any point P here which is at a distance R from the center, and at this point we are interested to calculate the electric field. Okay? Again we will take help of Gauss law, right? So for Gauss law we have to first define a Gaussian surface. So in this case the natural choice would be take a Gaussian surface which is spherical and centered at O, which is the center of the spherical shell as well. Okay, this is the now, because of symmetry on this Gaussian surface, all points on the Gaussian surface they are symmetrical with respect to the spherical shell, right? So because of this symmetry, electric field will be radially outwards, and it will be same at all the points. It will be same at all the points on this Gaussian surface. So let's take the value as E, and the area vector at any point if you take on this Gaussian surface, area vector is always normal to the surface. So the area vector will also be radially outwards. So in a nutshell, electric field and area vector everywhere will be parallel to each other. So angle between electric field and area vector would be 0. Okay, so now let's move ahead. Angle between E and A vector is 0. Okay, now we are doing the first case, which is point P is actually outside the shell. Okay, there is another case we'll do for point P is inside, right? So currently we are taking point P is outside the shell. Okay, what do I mean by this? The point P is actually outside the shell. Inside the shell is this, outside is this. So point P is outside. So considering this, net flux would be what? E into E dot A. So EA cos theta is 0. I've shown you. So E into A. So E is E, and the area would be area of the entire Gaussian surface, right? Total flux, this Gaussian surface. So it will be E into 4 pi r, small r square. This is small r, right? This is small r. So as per Gauss law, net flux should be what? Net charge upon epsilon naught. So net flux is E into 4 pi r square. This should be equal to net charge. The total charge inside this Gaussian surface is basically the total charge on the sphere itself. You can see that. Inside this Gaussian surface, this entire sphere is there, shell is there. So all the charge which is there on the spherical shell is inside the Gaussian surface because this point P is outside, right? So that means the net charge would be capital Q. Net charge is capital Q upon epsilon naught. So E would be Q upon 4 pi epsilon naught R square, right? So this is the formula for electric field of a spherical shell outside the shell. Okay. Now if you see this formula carefully, if I had given you a point charge Q which is kept at the center, if I had, instead of this shell, I had given you a point charge capital Q which is kept at the center O, right? You would have got the same electric field, 1 upon 4 pi epsilon naught Q by R square, point charge. So for all the points outside the shell, the field due to its uniformly charged shell is as if the entire charge is concentrated at the center, right? So sometimes the proof is put up like this. When this derivation comes, they give the problem statement like this. It proves that a uniformly charged spherical shell behaves as if the entire charge is concentrated at its center. So you have to do the same derivation and put these statements. Okay. So this was the case 1, which is point is outside the shell. Now what happens when point P is inside? right? There is no change in the flux calculation. Let's say electric field is E, so E into 4 pi r square. Now this r is this, Gaussian surface is now this, it is inside, right? The change would be now what? When you write this flux is equal to net charge upon epsilon naught, what is the charge? Inside this Gaussian surface, do you see any charge? All the charge is outside the shell. There is no charge inside the Gaussian surface, because this charge on the surface of the sphere here, right? It's a spherical shell. It's hollow inside. So there is no charge inside the Gaussian surface. That means this flux has to be 0. That means E will be 0, because 4 pi r square cannot be 0, so E has to be 0. That means for any point inside the shell, because it doesn't matter now wherever the point is, if as long as it is inside the shell, there will be no net charge. So for any point inside the shell, electric field would be 0. So if you draw a graph of E versus R, it would look something like this. Let's say this is the center of the shell. The starting point is the center of the shell. Until you reach R is equal to capital R, that is the radius of the shell, there is no electric field. But the moment you touch R, the electric field would be Q upon 4 pi epsilon naught R square, and from there onwards it will reduce, because it is a inverse square relation, Q upon R square. So it will reduce like this. So if you go very very far from the shell, the electric field will approach to 0 value. Okay, so this is this derivation. Okay, thank you.